Torque is one of the most important ideas in rotation of motion and is also one of the most misunderstood. If you've ever wondered why it's easier to open a door at the handle instead of near the hinge, or why some forces cause rotation whilst others don't, torque is the reason. In this video, we're breaking down torque from the ground up so you can solve even the hardest physics problems with confidence. So let's start off with the definition of torque. So torque is the tendency of a force to cause rotation. What does this mean? It means that you have a force applied somewhere, and then by exerting this force, let's imagine you have a force here, and by exerting this force, you are causing the object to spin around or to rotate around its around its axis of rotation, not center. That is something different. Axis of rotation. So now, what do all of these variables inside of this equation represent? So let's start off with T, or tau. So this is torque, and it's measured in units of newtons times meters. This is R, which is the distance from the axis of rotation. R is going to be, let's represent this as R. This is going to be R. F is going to be the applied force. Let's make this our F. And the theta is going to be the angle between R and F. So R and F are right there. That's going to be the radius. The angle is going to be like kind of like that. Well, so now, and the important idea that you have to know from this is only the perpendicular component of force causes rotation. So this more correctly should be labeled as perpendicular because it has to be a perpendicular force that causes rotation. So the force is already broken up into components. As you can see here, torque is just equal to the radius perpendicular to the force. And also, you can also use the geometry to find the lever arm. Torque is equal to the radius times the force that's perpendicular. So again, we can talk more about the lever arm. More about the lever arm is that, let's actually move this down a little bit and discuss this a little bit lower. So let's talk about the lever arm. A little bit messy, but it's okay. So the lever arm is the perpendicular distance from the axis to the line of action of force. So as you see here, torque can be written as tau can be written as FL, where L is the lever arm. And also the direction of torque. These are conventions. So counterclockwise is positive and clockwise is negative. So that would be pushing the right end of the beam upward. So let's actually draw these out. We'll get down here in a second. Let's see, clockwise is going to be positive, counterclockwise is negative. So let's see, you have a beam like this, right? Your beam, your beautiful beam. So if you push the right end upward, like here you have your force, and your force is perpendicular, right? And then the right end goes, if you push it downward, right? This is going to be at an angle. That's the angle, and this is the angle. So this would cause the whole entire thing to move this way, and that would be counterclockwise. And then this would cause the whole thing to go this way, which would be negative. So now let's talk about net torque before we get into some problems. So net torque is going to be, net is going to be the sum of the torque. And objects rotate only if net torque is equal to 0. So, an idea that you have to know is that a force can be large and still cause no rotation if it acts through the axis. So this explains why pushing at hinge doesn't open a door. This is because there's no radius. This is also why forces parallel to radius create 0 torque. That's because theta is just 180 degrees. And then sine 180 degrees is equal to 0. And this is why axis choice is critical. So what does torque depend on? Well, torque depends on the force magnitude, the distance from the axis, also the angle of application, because those are all involved in the formula. Those are all from the formula. A force F is supplied perpendicular to a rod of length L pivoted at one end. Find the magnitude of torque about the pivot. So here's the pivot, and it's applied perpendicular to here. So that's here, that's F. So we know that tau is equal to R times F sine of theta. Here R is going to equal to L. And theta is equal to 90 degrees. So therefore we have tau is equal to L times F sine of 90. Sine of 90 is just equal to 1. Tau is just equal to L times F. So therefore, perpendicular forces produce max torque because it's just being multiplied by 1. A horizontal rod is pivoted at its center. A force F acts upward at the right end and a force F acts downward on the left end. That's the pivot. The pivot's actually at the center. So it goes up at the right end, F, and F goes down on the left end. So you want to find the net torque. So torque from one force, that's just going to equal to tau is equal to L over 2 times F. Now the direction is the same, caused by both forces. So essentially, they're all going to make it go counterclockwise. So therefore, now we can calculate that the net torque is just equal to T net, which is just 2 times L over 2 times F. Therefore, we have that T net is just equal to LF. Torque doesn't cancel. So direction matters, not just the force direction alone, both the directions. A force F is applied at a point on a disk that acts directly through the center of rotation. What's a torque about the center? Again, torque is RF sine theta. That's equal to 0 here, and sine of 0 is equal to 0. So therefore we just have tau is just equal to 0, theta is equal to 0. So therefore we know that large forces can produce 0 torque if applied through the axis. That would also mean that the radius is equal to 0. Torque causes rotation, not force alone. Lever arm matters more than the force size. Perpendicular forces give maximum torque. Forces through axis give 0 torque and always track the torque direction.